Hi everyone, my name is Shin. This is my final project about optimizing tiny ImageNet classification accuracy using Inception V3 model. I choose Inception V3 because after some comparison between different models for the ImageNet starting from 2012, such as GoogleNet, AlexNet, even like VGG, I find like Inception V3 outperforms all of them in terms of accuracy and efficiency. So Inception V3 was invented and published during the 2015 by Google. Uh, at that time, it was using RMS prop optimizer. I actually find some potential to improve with the like such as the training data, the optimizer. So that's why I choose this project. First of all, I will introduce something about some advantage of this model architecture. So in terms of the Inception V3, it has like right here over 48 layers. It includes softmax layers, convolution layers, batch normalization layers, a lot of things. One specific thing for Inception model is it's in the E-Inception optimizer. You can see it from here. Uh, it might be not very clearly, but its basic concept is like doing some optimization. Instead of like direct feed forward, it's like doing several different convolutions and porting to extract the great features of the image, which save a lot of time. Also, a nice thing about Inception V3 is we call transfer learning. What is transfer learning? Because it is Inception V3 trained the ImageNet, which is like over 10 billion, 10 million datas. So like the weights are collected on a 2048 dimension vector. So these are the weights which help used for later purpose, such as for me, tiny ImageNet. Because of the I'm choosing tiny ImageNet because of the GPU limit. Also, the dimension of tiny ImageNet is 64 by 64 by 3 compared to the ImageNet 256 by 256 by 3. So the dimension like actually has the same ratio. That's why Inception V3, the transfer learning, has been a nice model to do that. Okay, basically after talking about some advantages, I will talk about some improvements of this specific model. It is using batch normalization accelerate because for large data, it needs more computation to realize the goal, but if we normalize it to close to zero, it will save much more time. Also, in Inception V3, it has included a method called factorization into smaller convolution. We can see it from here. It costs a lot of things to do 5 by 5 convolutions, but actually, if we take two 3 by 3 convolutions, I specified I make an example and very specific about like how much it improves the efficiency right here. So actually, two 3 by 3 layers can do the same thing as the 5 by 5, but it can actually save a lot of time and work. So these are like most of the things Inception V3, which is like has more advantage compared to other. Also, one more thing. So let's come to the main topic, uh, where I can do some improvements. Inception V3, as I mentioned before, it was published during 2015 and used RMS prop optimizer. So, but after that, there are some more advanced optimizers such as Alan optimizer, and there's also Nestop because like the later two add more smoothing in the like training process, which in most cases they have better results. So what is my goal? What is my goal of the accuracy, top one accuracy in terms of the tiny ImageNet? There are not much more papers published about this. I take a reference from a Stanford student which he reaches 74.5 accuracy. and he's using the sampling method to like reach that accuracy. So this is like a comparison. First of all, what I'm doing is that I try this three most advanced optimizer by doing some by like trying different parameters. I basically setting the same most like optimal settings for PCA for training batch size, test batch size, learning rate, epsilon, this kind of thing. And this is some data I get. Mostly the Nestov when it converges, it has about 74% accuracy, so it's a little bit lower compared to the result get by the Stanford student. So I'm thinking about like since some problems like the tiny ImageNet, because there are only like 200 classes and each only have 500 images to train. So I'm wondering like if overfitting will be an issue with that. So I'm doing data augmentation. Here you can take a look. This is the original image. I'm adding some Gaussian noise to it, which make it look different, but you can see this is still a fish. I can also do a flip, which does not like affect classification. And also I can add noise to the flipped image. So by doing this, I reconstruct 200 samples for each class, which overall I have 140,000 samples for training. And also like some data seems like a little bit weird. That's what kind of affect the pre-trained transfer learning rate on the 2048 dimensions. But anyway, I still like give a try for this for like this the whole data set. But the result is not quite ideal for me. The Nestov optimizer like achieve most like the similar result accuracy compared to before, but in terms of Atom optimizer and IMS prop optimizer, their accuracy is compared like a bit lower, especially the Atom optimizer. It has a serious overfitting issue, but you can see like from the beginning, because like some early training for Atom optimizer and Nestov optimizer can actually receive a higher accuracy. So that's why. So why? Because like some extra data actually like provide some important features for data to do like correct classification, but overfitting issue still exists. Even though I add 200 samples like for each classes, there's still overfitting issue. So let's talk about the future. Now generative adversarial network has come out, and like you can generate a lot of real representative pictures. So with the help with that, we can generate more reliable data to overcome this kind of overfitting issue. And there's a lot of space, like in general, in terms of the ImageNet computer vision area. Because so what should we do in the future? We should not just like trying to advance more on the architecture convolution network, but also we need to like take more thinking in terms of using some mathematical theorem skills to like manage the data, to like do some data augmentation. This is also a nice approach for us. So basically that is all what I have done. Thanks for watching.